Today we're going to talk about exponential function. Exponential function in format looks like a to some power x. If you remember, polynomial is in the form of x to some power constant, 2, 3, whatever that exponent is. Exponential is the other way. It's 3 to some power. So it's the base that is the constant, the exponent is the variable. Normally we write this a to the power x, and a as the base, we assume it's it's a non-negative number. It's a positive number. If you pick 0, then 0 to any power is 0. So we avoid 0 as well. So all positive numbers. As well as if you pick 1, 1 to power 2, 1 to the power 3, 1 to the power 4, doesn't really make any difference. Still always 1. So we avoid the case of base being 1 as well. So this, when I say a is not equal to 1, just is that for that reason. And negative numbers cause some problem, as square root of a negative number is a complex value. So when we discuss these functions, we avoid negative base as well. So functions, exponential functions, normally we discuss it with positive base. Okay, let's look at a couple of examples. For example, f of x equal to 2 to the power x. That's the simplest function. You can calculate. If I ask you what is f of 3, then you say this 2 to the power 3. What is 2 to the power 3? Simply 8. So there should be a point, 2 and 8 on the graph. Sorry, 3 and 8 on the graph. What if I ask you what is f of 0? Okay, 2 to the power 0. Any constant to the power 0? 1. Except 0 to the power 0. 0 to the power 0, this is undefined. That's maybe one of the reasons that we assume the base is positive as well. Okay, so 2 to the power 0 is 1, 3 to the power 0 would be 1. I can say a to the power 0 is 1, assuming a is not 0. Okay, it could be negative to the power 0, still 1. How about f of negative 1? If you replace negative 1 into the exponent, what do you get? 2 to the negative 1 equals, you can write this as positive exponent, 1 divided by 2 to the power positive 1. You can move this to the denominator, make the exponent positive, 1 over 2. Okay, you might have forgotten why these are true, but here let me show you maybe the reason for it. This is basically the idea. If you have x to the power 5 divided by x to the power 2, what does it mean? It means x times 5 times divided by x times x. And you would cancel and say these two will cancel out, those two will cancel out. What is left is basically 3x's. So you can write it as x to the power 3. But the shortcut would be, okay, you can subtract the exponent. x to 5 divided by x squared means x to the power 5 minus 2, which equals x to the power 3. How is that related to here? Think about it this way. What if it was x to the power 2 divided by x to the power 3? In one sense, you can simply say this is x to the power, let me make this x to the power 5, just so you can see. X to the power 2 divided by x to the power 5, you can cancel out the x's and say this is x to the power 3. What if you subtract the exponent? You say x to the power 2 minus 5. What is that? X to the power negative 3. So I can say x to the power negative number is the same as 1 divided by x to the power positive number. This is the same as saying 2 to the power negative 1 is the same as 1 over 2 to the power positive 1. That's what I wanted to get to. It's just basic division. You can extend it and use it this way. What if I ask you what is f of 1/2? You should say, okay, 2 to the power 1/2 means, you remember fractional exponent is square root of 1/2. X to the power 1/2 was the same as square root of x. X to the power 1/3 would be cube root of x. How about x to the power 3/5? This is 5th root x to the power 3. So if you say f of 1, let's say 3/5, this means 2 to the power 3/5, which means 5th root 2 to the power 3. It's not a nice number, you'll end up with a decimal value, but the way that you calculate is you can turn it into fifth root, cube root, third root, whatever the fraction is. So it's important to know these properties. This is one of the properties. The general form is if you have x to the power a divided by b, this is b root x to the power a. Okay. Normally, you can graph these functions as how we graph polynomials and stuff. You can always pick certain values. So here I'm going to say, for example, I'm going to try to graph to the power x. Let me erase some of this stuff on the right side. Yeah. Okay. Create some space so we can graph the function better. Okay, my computer for some reason is super slow at the moment. Okay. System is frozen. That was a mistake. Okay, so let's pick x and y values. To graph to the power x, you would pick 0, 1, let's pick -1 and -2 as well. Couple of positive, couple of negative values. I can pick 2 as well. If you pick 0, replace it in the function, you get 2 to the power 0. We already calculated that. Sorry about this. 2 to the power 0 was 1. 2 to the power 1 would be 2. 2 to the power -1, 1/2. 2 to the power -2 is 1 divided by 2 to the power 2. This would be 1/4. And here 2 to the power 2 would be 4. So if I want to graph 2 to the power x, I can say basically, how does 2 to the power x looks like? Let's pick a couple of points. It's a 0, 1. This is 1. -1 and 1/2. So 1/2 somewhere here. Okay. 0, 1. -1 and 1/2. -2 and 1/4. So let's say somewhere here. Then you have 1 and 2. And 2 and 4. Somewhere here, 4, for example. Okay, so connect these points. Draw a curve that's going through these points. You'll see that it looks like this. And if you go on more and more, you'll approach this x-axis. So this is the structure of 2 to the power x. This is how 2 to the power x looks like. One important thing that you should notice is that this x-axis, we call it the horizontal asymptote in this case. That means the graph of the function approaches to that x-axis, but it never touches the x-axis. You never cross that x-axis. It approaches the x-axis at some point in infinity, in negative infinity. We assume, okay, it may reach there, but it never reaches there in that sense. It's just approaching to that x-axis. So we consider the x-axis to be an x-axis here, x-axis, to be a horizontal asymptote. What is the equation of the x-axis? Is basically y equal to 0. Okay, so sometimes they ask you for asymptote. In this case, there's an asymptote, horizontal asymptote. It's basically the x-axis. And one more thing that you should notice is you can graph other type of functions based on 2 to the power x. If I ask you what is the graph of f of x equal to 2 to the power -x looks like. And just because you have 2 to the power x, you should be able to draw 2 to the power -x. If you remember in the transformation section, we discussed that if you change the exponent, if you change an input, you change f of x to f of -x, compare f of x to f of -x, the transformation correspond to this would be a reflection. And what reflection? It would be reflection about y-axis. So what does it mean? That means if you have the graph of 2 to the power x, the graph of 2 to the power negative x is just reflected about the y-axis. So it will look as if we draw this. Still, you have the horizontal asymptote to be the x-axis. This is still the horizontal asymptote. But the graph is now, instead of being increasing, it turns out to be a decreasing graph. And you can generalize this. By the way, 2 to the negative x, you can think about that as 2 to the negative 1 times x. I'm going to write it this way, 2 to the negative 1 x. I can show you another format. 2 to the negative 1 is 1/2. 1/2 to the x. So the relation between 2 to the x and 1/2 to the x is basically that the function from being increasing turns out to be a decreasing. It's a reflection. So there is a general form to graph these functions. The two general form are, if you have an exponential function a to the power x and you want to graph that function, if the base is a number greater than 1, like 2, 3, 4, the function should be increasing and have to have a horizontal asymptote. So it will look like something like this. This is when the base a is greater than 1, like what we graph 2 to the power x. This could be 3 to the x, 4 to the x. It could be 10 to the x, doesn't really matter. It could be pi to the x. The base doesn't need to be always integer. It could be any other number. What if the number is between 0 and 1, like 1/2, 1/3? If you have 1/2 to the x, 1/3 to the x, 2/5 to the x, 1/pi to the x, all these exponential functions have the similar shape. What is the shape? It's a decreasing function. And this is how it looks like. You still have the horizontal asymptote to be x equal to 0, the y equal to 0, the x-axis. So the general shape of these exponential functions is very easy to see. You just need to figure out a couple of points. In this point here, the y-intercept in both cases, always 1. Because any number to the power 0 is 1. 1/2 to the power 0 is 1. 1/3 to the power 0 is 1. It means if you pick x equal to 0, what you get for the y value is always 1. This is if you're dealing with a to the power x. But sometimes you have a coefficient up front. Sometimes you will have something like -3 times to the power 2 to the x. What happens in those cases? You graph 2 to the power x, then find out through transformation what happens if I have a -3 there. So let's see. For example, this one, we want to graph it. I already know. I already know how 2 to the power x looks like. This is how 2 to the power x looks like. You remember, if you multiply 3, what happens? So here, that 3 times 2 to the power x is basically multiplying all the y values, multiply by 3. That's what happens. It was all the y values times 3. This means you're stretching the graph along the y-axis. You're rescaling the graph. So what happens if you do that? This 1, 0, 1 multiplies by 3 and it becomes 0, 3. If there is a point here 2, that point with the y value of 2, that point will rescale to 6. It'll be here. So all the y values get stretched. So the graph will somehow looks like this. You can pick a couple of points. You can say this is 1 and 2, 0 and 3. Becomes 1 and 6, 0 and 3. So you rescale all the y values. The x values do not change. What would be the next step? The next step would be, what happens if you multiply a negative number, negative outside? Step 2, if you multiply that negative times 3 to the power x. we already have the graph of 2 to the power x. If you multiply a negative there, this is as -1. You can think about that. If you multiply a negative, this is a reflection. True to transformation, we discussed this. Reflection about what axis? This is about x-axis. If you change the exponent to -x, then that would be a reflection to about the y-axis. But here you're multiplying a negative outside. It is like changing f of x to negative f of x. That's what you do. You multiply negatives to the function. You do not change x to -x. You're just multiplying a negative. In that case, you have a reflection about the x-axis. Now I reflect the graph. I'm going to draw it here. If I reflect it, what do I get? I'll get this graph. This becomes -3, and you will have -6. That point exactly would be reflected to -6. So basically this black graph is, sorry, draw this better. This is f of x equals -3 times 2 to the power x. We can do that for every other function. If there was a +1 at the end, what would happen? If there is a +1, then you shift it up 1 unit. This graph will shift up 1 unit everywhere. And what happens to the horizontal asymptote? The horizontal asymptote as well will shift. Instead of being at that x-axis, now the horizontal asymptote happens at 1. So what happens to the horizontal asymptote is at y equal to 1. This would be the horizontal asymptote. This is if you have this +1. If you have -5, you shift it down 5 units. These are all through the transformation. So if you know the transformation, you can graph these exponential functions. Basically, what you need is just the structure of this 2 to the x. And rescaling, shifting up and down, these are just simple calculation. Okay, always you can draw tables and pick numbers as well. That's not an issue. I'm just showing you different ways and faster way to calculate. Okay, these are calculation of exponential, but before I go to show you what is this exponential used for, I'm going to mention this e. Similar to a pi, this is a number that does not stop. It continues on going, 2.71828 something. I don't remember exactly. So this is similar to pi. As you say, pi is 3.141592, I think. I don't remember. 926, 962, something like that. What you see is this is going to be useful. Exponential e. Normally it's for the exponential function. This e is very common. It's very commonly used as in nature. When like a bacteria or something repopulates, this e shows up in the repopulation model. So you will see this e very commonly used in your textbooks for other classes as well. But how about the use of it for our class? Let's consider this word problems. We'll go through them. Simple interest and compound interest. This is something that you can use it in your daily life. Let's say you go to the bank and you borrow some money and they give you an interest rate and say, well, how much money at the end you have to pay back. We're going to do this calculation. So it's very important that you can use it in daily life just to understand which case is better. Okay, so let's understand some information. First, suppose $P is what the amount that you're investing or you're borrowing. So principal amount that is invested or borrowed. I'm going to call it P. And the annual interest rate. The interest rate, we pick a notation R. So R represents the interest rate. And T, number of years. So you borrow money, a certain amount of money. That's the $P that you borrow with the interest rate of T, or interest rate of R for T years. Then what is the interest rate? There are certain ways to, the amount of interest. There are certain ways to calculate the amount of interest. The simple one is that, for example, you borrow $200 and I'll tell you the interest rate is 1%. That means every year you get 1% of that 200 as an interest. So 1% of the 200 is $2. So plus $2 every year. So first year you'll have $202. Next year you would have $204, and so on and so forth. This is called a simple interest. Simple interest is just the amount that adds up every year. So if you have $100, let's say P, multiply $200 P, multiply by the interest rate 1%, that's $2. T years after, so you do this for 5 years, for example, you'll get $2 every year. Multiply all those together, you'll get $10 at the end. So the interest amount that you get at the end, it's $10. So this is assuming that interest rate is simple interest. It's very important to know this term, simple interest. That means there is no adding up the interest every year and calculating that. The other way of interest is that, let's assume you have, so this is, let me show you an example as in front of each one. Let's say you have $200 and every year they give you 1% interest. So I'm going to write 1%, multiply by 1%. 1% is the same as 1 over 100. This is 1%, right? And for 5 years, what you get is 2 times 1 over 100, 200 over 100 is 2 times 5, 10. This is every year you'll get 10, at the end of 5 years you'll get $10 if you invest $200 with 1% interest. So at the end, how much money you have is $200 plus $10, $210. That's the total amount. But there is another way, and say, what if I calculate the interest this way and say, first year I have 200, I'll put it in the bank. After 1 year, how much do I have times 1 over 100? This would be $2. Now this $2 will add up to my amount that I already have in the bank. It will be $202. Now I want interest over the $202, not only the 200, because I have an extra $2. So for next year, you'll get multiply by 1 over 100 again. You'll get $2.02. Then added up, you'll get $204.20. Now you'll see that after 2 years, you have an extra 20 cents. If you do the same process over and over, after 5 years, you will end up with, say, $211 or something, $11.06, something like this. Now you'll see that you have an extra $1.06 because every year you've added that amount of interest to your initial amount, principal amount. So what happens in this case is what we call it the compounding interest. It means the interest that you have adds up to the amount that you have every year, and you get interest over that as well. This is called the compounding interest. And this is if you assume this happens yearly. So what you get is just adding it up. But the compounding interest could be monthly, weekly, daily, depending on what the bank does. Normally the bank's doing it per year. If you borrow money, they do it yearly. So the formula for at the end result, how much money do you have? This A is the total amount at the end, the future result. Depends on R, which is the rate of interest. N is number of compounding periods. That means, do you want to do it monthly? That means 12 times every year. If you want to do it quarterly, 4 times and become 4. If you want to do it daily, 365, and so on. You can do it weekly, 52 or 54, 52 weeks. So N represents the amount, the compounding periods every year. So this formula here, A equals P times 1 plus R over N to the power NT, will have that exponential form because there is a base, there is an exponent. T could be a constant, T could be your variable based on how many years, you can have an exponential form. But in general, if this n approaches to infinity, that means instead of considering it 12 times a month or 365 times, if you change it forever, like every second, every millisecond, this would what we call it the continuous compounding. So every second you'll have an extra increase in the amount that you already invested. And the formula depends on that E that we mentioned, 2.71. If you let n approach to infinity, there is a formula that expression, this expression, could change to p times e to the power rt. All this stuff that I'm saying just to give you an idea of how these formulas coming about. We will use it to calculate, but it's good to know that at some point, if you borrow money, you can calculate it yourself to see, okay, which case is better for me. Do I want to go through simple interest? Do I want to go to compounding interest, continuous interest, depending on the interest rate? We'll do examples. So here, first example, ignore this red data. This is just because I already calculated. I don't want to go back to the calculator over and over. So first, suppose you have $10,000 investment. So what is P? I can say P equals $10,000 investment. Interest rate 4%. 4% is R. Don't write as 4%, write it as 0.04. 4 divided by 100 is 0.04. And for 5 years. So T is given 5. And we want to calculate the following compounding options. Annually, let me write the formula down. A equals E times 1 plus R over N to the power NT. The good thing for this class is that since it's online, you don't need to memorize anything. You have access to these formulas. Even though if it was in the class, I will provide the formula, but still better than looking through formulas to see which one is what. Okay, so the compounding option in this case is, first case, A, annually means let n equal to 1. 1 times a year. Once a year, you'll get that interest rate calculated. So here, let me show. So what do? You are looking for the total amount. A equals P, which is 10,000, times 1 plus 0.04 divided by 1 to the power N, which is 1 times 5. Use your calculator, calculate this. What do you get at the end is 12,166.6. I rounded up to 0.6. So this is what you would have at the end of 5 years. If you start with 10,000 investment, after 5 years, what you have is $12,166. So normally when you buy a car for like 10,000, at the end, if they tell you there's a 4% interest for 5 years, this is the amount that you're paying up. You're paying up $12,166. So you can calculate this, and they will divide this. Let's say they tell you that this is calculated in 5 years, and you have a monthly payment. They divide this by 30. I can 5 years is 60 months. If you divide that by 60 months, whatever you will get, let's say it ends up to be around $300 and something. $300, maybe $2, something like that. 166 divided, yeah. So around $302 monthly. This is what you would pay. But normally, what they tell you is this monthly. They do not tell you this total data, because you will see that how much you've already paid as an interest is 2,000 more than the initial data that you've put in. They tell you the car price is 10,000, but at the end you're paying 12,160. Okay, that's one of the examples. What if the interest rate was quarterly? What happens? Everything is the same. The only difference is now instead of n being 1, n turns out to be 4. You're paying interest 4 times a year. So what happens? A equals 10,000 times 1 plus 0.04 divided by 4 to the power 4 times 5. And what do you get at the end? Is 12,201.9. If you compare this two numbers, it was on this one. Ignore the divide by 60. Let me erase this part. Okay. If you compare these two, you'll see that if you get interested quarterly, what you're paying is it's going to be more. The interest happens every quarter, means those interests will add up more. What if it happens continuously? Continuously, the formula changes. A equals e to the power RT, and E is that exponential 2.71. So what you get is A equals 10,000 times E. Don't write it as 2.7. Your calculator has E already. To the power R, which is 0.04 times T is 5. You calculate this, you'll end up with 12,214. And now, if you compare this with the quarterly, you'll see now you're paying more interest as well, even more than the quarterly. And this is actually the maximum of the interest amount that you are paying. If with the interest of 4%, this is the maximum. You cannot get higher interest out of it. Okay, here's one more example. They are very similar, but this is maybe a better option just to understand in your daily life. Al needs to borrow 15,000 to buy a car. It's very common. You go to buy a car, they ask you, you have 15,000 as the price of the car, or whatever like that. And they tell you there are two options. 6.7% simple interest for 5 years. This is one of the options. The other option is 6.4% lower interest rate, but it happens continuously over the 5 years. These are the two options. And we want to figure out which one is the best case. So first, figure out how much is, the first part is, they ask you how much total interest would you pay without pay at 6.7% simple interest. If you remember simple interest, I is the total interest. Interest would be 15,000 times P times R times T. This would be I. This is the total interest that you're paying. 15,000 times R, which is 0.067, 6.7 divided by 100. This is the R times T, 5 years. What would you get? Again, ignore this red. This is exactly what I calculated earlier. So what you get is 5,025. This is the interest that you're paying back to the bank for $15,000 borrow. So if you borrow $15,000 with simple interest of 6.7, you're paying an extra 5,000 back at the end. This is just the interest. If they ask you what is the total amount would be 15,000 plus 5,025. How about if you consider the other case? If it was 6.4% interest compound continuously. Continuously was A equal P e to the power RT. So what is A? A equals 15,000 times e to the power 0.064, 6% interest, times T, 5 years. If you multiply this out, what you get at the end is $20,656.9. Okay, so this is the total amount. So what they want is the total interest. How much is the total interest? You already have 15,000, so you have to deduct the 15,000 from it. So the interest would be 20,656.9 minus 15,000. You'll get 5,656.9. This is the amount of interest that you're paying on that $15,000 loan for 6.4% interest rate compoundedly. So which case is the best? The last question is which option result has less total interest? That would be the best case for you. So in this case, you compare the interests. Definitely in this case, it's obvious that 5,025 is much better than 5,656. And you'll see that even though this has higher rate of interest, since it's simple interest and they do not add up to each other, you'll see that the interest that you're paying at the end is lower. So do not just see the numbers always and say 6.4 is better. It's just you have to calculate and figure out which way is the best. Sometimes this is the way that the banks will give you misleading information, is that they don't tell you exactly which way they're calculating. So they tell you there is a higher interest rate. Let's say you're investing a certain amount of money, they tell you there is a 7% interest rate, but they don't tell you that it's basically a simple interest rate. So the interests do not add up to each other. This way you're missing on your investment. So make sure that you know this topic because it's useful in daily life. Okay, I'm gonna stop here. Hopefully it's clear. Try a couple of examples as well.